Hi, College Algebra. This is Mrs. Kelly here. We are going to start your Chapter R notes, which is your review chapter for the beginning of the school year. The first thing we want to do is make sure that you have your yellow packet of notes that I gave you on Thursday, and that's where you'll find all the notes that you're going to take for the entire Chapter R. So if you look at our first algebra and real number set for day one, we're going to talk about set notation and the classification of number sets. So if you look here, we have a list of all these terms in this left column. What I want you to do right now is go ahead and copy down these definitions. So if you need to pause the video right now, go ahead and do that. And when you return, we'll talk about the examples of such definition and the symbols that go along with it. Okay, so hopefully you are back and you wrote down the definitions. So let's talk about what a set is. A set is a group of numbers or terms. And when we talk about a set, there's a symbol. It looks like a fancy parentheses, or we call them braces. So if you're worried about, oh my gosh, I don't know how to do that, don't worry about it. As long as you make little squiggly lines, do the best that you can. So when we see this symbol, we are talking about a set. Now, an example of a set is going to be named by a capital letter. So for example, if I say the set A contains these numbers, 1, 3, 5, 7, and 9, these are all part of that set A. An element is an object or term in a set. So we're going to use this weird looking E for the symbol of an element. So for example, if you look here, I have all of these numbers in set A. I could actually say that the number 3 is an element of set A. If I also make another set, let's say I'm going to make set D. Again, we define a set with a capital letter. And let's say that set D contains the letters A, B, C, D, and F. Notice that the elements in the set are used with lowercase letters, where the actual name of the set uses a capital letter. So for example, I could say that F is an element of set D. So these are just some examples of what elements are. The 3 and the F are both elements of set A and D respectively. All right, next, an empty null set is a set that contains no elements whatsoever. So if there's no elements within the set, then we're going to leave it empty inside. So sometimes you'll just see the braces by itself, or you could use a 0 with a line through it, and we say the empty set. So if I were to ask you, what are all the even numbers? In set A? Well, if we look at set A, these consist of all odd numbers. There are no even numbers. So therefore, it's the empty set because there are no elements of even numbers in set A. All right, next is a subset, which is a set that contains values of another set. So the symbol for that is a sideways U, or a hyperbola. And if I made another set name, B, for example, let's say that set B is made up of the elements 5, 7, and 9. Well, notice that these elements in set B are also elements of set A. They're all contained within set A. So then I could say that set B is a subset of set A. What if I asked you, is set A subset of set B? Well, you have to ask yourself, are all the elements of set A in set B? Well, the answer is no, because I'm missing the 1, the 3 in here in set B. So unfortunately, B is not a subset of A. So if I wanted to write that notation, I could say, actually, I meant to say A is not, which is a line through it, a subset of B. All right. Next, let's talk about the listing method. Basically, a listing method is a list of values. So we're taking these values here. So basically, I'm asking you to list all of the elements inside. So my values, for example, are 1, 3, 5, 7, 9. So really, you're listing them without actually naming the set. So you're just missing the name of the set here. All right, let's move this up so we can see. All right, so next we're going to talk about the rule method. So the rule method is basically the notation that indicates a rule of the terms of the set. So for example, if I want to say the set of all x values such that x is an even number between, let's use 2 and 10. All right. So your symbol for that is starting with the set of all x values such that x dot dot dot, whatever you want that rule to be. So in this case, the rule was it's an even number between 2 and 10. So then you would list all the even numbers between 2 and 10. All right, so those are your definitions. And now let's talk about some examples. So some important aspects to consider is if we have two sets A and B and all the elements of A are in set B, then A is a subset of B, which we talked about already. We showed you that an example. All right, and then next, the empty set is a subset of all sets. Now, it's hard to imagine this, but we know that the empty set has no elements within inside it. And because it has no elements within inside of it, it's also an element of any given set. So therefore, it has to be a subset of all sets. Next, if two sets have the same elements, then they are equal sets. So for example, if you look, set A here has the elements of 1, 2, and 3, and set B has the elements of 3, 2, and 1. Well, then set A is equal to set B. Okay, let's look at some examples. We're going to answer true and false about this. It's really important that you get down the notation. So this E stands for element. Here we have this sideways U, which is your subset. And again, this is our null set or empty set. So let's look here at letter A. I'm asking you, is the number 3 an element of this set listed here? I don't see any 3s, so unfortunately, that's false. What about this one? Is -1 an element of this set? Well, we can see that -1 is contained in that set, so that is true. What about 1 and 2? Are they a subset of 1 and 2, 3 and 4? That set, it is true. All right. Next, let's look here. Is 4 and 7 a subset of this listed set? Well, 4 is, but not 7. And for this to be true, all the values would have to be included. So that is false then. Next is the empty set an element of 5, 8, 9, and 14. This is going to be false because there are no elements in the empty set. And unfortunately, these are the only elements in this set here. However, is the empty set a subset of this set here? It is, because remember we said that the empty set has no elements, so therefore it is a subset of all sets. So this is true. Okay, let's move on. You turn the page. Now here they want us to describe each of these in the listing method. Using the listing method, before we talk about integers, we want to go ahead and describe those and what they look like with the symbol and then define those. So first of all, there's natural numbers, and the symbol for a natural number is a double stemmed N. And the definition or examples are your counting numbers. So think about if you're standing still and all of a sudden I say move forward and count your steps, what number are you going to naturally start with? Well, you're going to start with 1 and 2, then 3, and so forth. So your counting numbers naturally are 1, 2, 3, 4, and on and on and on. So those are your counting numbers. And they're whole numbers because you naturally count whole numbers. All right, integers. Well, here's a symbol for integers. It's a double stem Z here. All right. And those are our natural numbers, which are your 1, 2, 3, 4, and so on, but also the opposites and 0. So we're going to include 0, including 0. So for example, we know the list goes on and on with negative. So -2, -1, 0, 1, 2, and forward. Okay. Rational numbers, the letter Q, and it's like a little double stem Q there. You're like, well, why doesn't it have the R? Well, that's because we use the double stemmed R for real numbers. So we use Q for our symbol for rational numbers. So those are numbers that can be written as fractions. And when we think about that, we have to be careful. It can't be just any number. It has to be like an integer form. It has to be repeating or terminating decimal. So for example, 1/2 or 1/2, 6.425, that is a terminating number, or 22/7. All right, those are whole numbers, and um, those can be written in integer parts. So for example, we can't use pi over 1 because even though 1 is an integer, pi is not, and that's not a rational number because that does not terminate. All right, so that's a non-example. An irrational number, oh, we have a capital I, double stemmed. Those are numbers that cannot be written as fractions. All right, we're going to emphasize cannot. So those are your numbers like pi. Even though pi is 3.14, we round it to 3.14. It actually goes on and on to infinite numbers. The square root of 5. If we took the square root of 5, it's not a perfect square. However, if we took the square root of 16, for example, the square root of 16 simplifies to 4, and 4 is a rational number. You just have to make sure that the square root of radicand inside cannot be simplified anymore to an integer. If I'm going to take the cube root of 8, well, the cube root of 8 is 2, and 2 is a rational number. But the cube root of 7 is not, because I can't take the cube root of 7 without it being written as a fraction. And I'm going to move this up here so we can talk about real numbers now. And believe it or not, real numbers are all of these above numbers. All right, so here's our double stemmed R. That's the symbol for real numbers. All of the above. That includes all our natural numbers, our integers, our rational and irrational numbers. All right, so taking that and knowing what we know about integers now, let's go ahead and try these examples. Here they want us to write each set being described using the listing method. All right, well, using the listing method, they want us to find the set of all x values such that x is an even integer. Remember what an integer is. It's all our natural numbers and their opposites in 0. So find an even integer between -5 and 7. So since I'm using the listing method, I know I need my braces. Integers between -5 and -7. That's an even number. Well, -5, we need to start increasing our value. So -4 would be an even integer. The next even integer would be -2. -1 is not even number, it's odd. 0 is an even number. Remember that any number ending in 0 is even, so that includes 0 itself. We have +2, +4, and +6. And since we can't go any higher than 7, that's as far as we can go. Using the listing method, those are the set of our x values. Next, let's find the set of all x values such that x is an odd integer between -2 and 12. Well, if I'm looking for odd numbers between -2 and 12, -1, 1, 3, 5, 7, 9, and 11, as far as we can go. Can't pass 12. Why don't you try this I on your own and pause the video right now. All right, hopefully you're back. And hopefully your vowels, you got A, E, I, O, and U. Now I know the rule is sometimes Y, but because it's not always Y, we're going to leave Y out of it. All right, moving on. Now you want to try on your own. Use the listing method to show the set of all x values is a multiple of 5 between 7 and 48. So go ahead and try that one right now on your own. Pause the video, please. Okay, welcome back. So hopefully you saw that if it has to be a multiple of 5, then it either has to end in 5 or 0. And since it has to be between 7 and 48, well, that leaves us starting with 10, 15, 20, 25, 30, 35, 40, and 45. This is the listing method. All right, next, this is a yes or no question. Is 5 an element of this set? You can see that it is. So this is true or yes. Next, this should say our natural numbers. Is it a set of integers? That should be Z. Yes, it is, because every natural number is also an integer. All right. And last but not least, is the empty set a subset of this set here? Yes, it is, because remember, it's kind of a tricky question. There are no elements in the empty set. So since empty sets have no elements, every element of the empty set is also an element of every set. All right? Okay. So from this point on, what you're going to do, we finish the notes for day 1, and we're going to move on to day 2 notes in a second. So